We've all heard it. Throw more GPUs at a problem and AI scales, right? Well, not anymore. At least not if you're doing long context inference. Here's the truth. For LLMs with hundreds of thousands or even millions of tokens, GPUs aren't the bottleneck. Memory is. Today we're talking about NVIDIA's Inference Context Memory Storage, ICMS, a new memory tier designed for AI inference that actually lets your GPUs breathe.
So let's start with the mechanics. Transformer models don't just process a token and move on. Every attention layer stores key value pairs for each token, what we call the KV cache. Now, KV cache scales linearly with the sequence length. That's simple math. The KV cache size is approximately equal to the number of tokens multiplied by the hidden size of each layer, multiplied by the number of attention heads, multiplied by 2 for the key and value matrices, and finally multiplied by the size of a 32-bit floating point number. For example, a 30B parameter model running a 2 million token context, we're talking terabytes of KV cache. That's bigger than a typical HBM capacity on GPUs today. So what happens? You spill to DRAM. DRAM can hold more, but it's slower, and replicating this across multiple GPUs or nodes multiplies the problem. Recomputing KV cache, it's basically burning GPU cycles for no reason. You end up bottlenecked by memory movement, not compute.
Here's the classic memory stack for AI inference. 1. GPU HBM, ultra-fast, very small. 2. System DRAM, bigger, slower. 3. Local NVMe SSD, even bigger, higher latency. 4. Enterprise storage, huge capacity, slowest. Latency gaps are huge. HBM is nanoseconds, DRAM is tens of nanoseconds, SSDs are hundreds of microseconds, and network storage hits milliseconds. When context sizes explode, GPUs spend more time waiting for KV cache than computing. This is why people see underutilized GPUs in large AI factories. The memory hierarchy is throttling throughput.
This is where ICMS comes in. NVIDIA designed it as a new memory tier, sometimes called the G3.5 tier, to sit right between DRAM and enterprise storage. It's optimized for high throughput, low latency, ephemeral, recomputable data like the KV cache. Think of it like a shared super-fast cache that multiple GPUs can access simultaneously. Instead of every GPU hoarded its own KV cache, ICMS allows shared access across nodes, dramatically reducing duplication and memory overhead.
Here's what really makes ICMS tick. It's the BlueField-4 DPU. It offloads a ton of tasks from the CPU. Memory orchestration for KV cache, prefetching tokens into DRAM before GPU demand, low-latency network communication using RDMA. The result? Memory movement happens mostly off the CPU, and GPUs stay busy computing. In practice, an ICMS-enabled pod can cut GPU idle time from 30 to 40% down to under 5%, a huge jump in tokens per second and tokens per watt.
Let's put some numbers on this. Scenario: 30B model, 2 million tokens, and 8 GPU pod. Without ICMS, GPUs idle 25 to 40% waiting for KV cache. With ICMS, idle less than 5%. Throughput improves 3 to 5 times. Tokens per watt improves 2 to 3 times. This is huge because inference efficiency now depends more on memory hierarchy design than raw compute.
This changes how we design AI factories. Distributed memory tiers, HBM to DRAM to ICMS to storage, memory-aware scheduling, prefetch and eviction policies, context-aware orchestration only move relevant KV slices. If you're designing multi-node inference clusters, you can't just think about GPU count. You have to think about how KV cache moves through the memory hierarchy. ICMS is effectively telling us to scale LLM inference, memory first, compute second.
So, the next time someone says more GPUs equals more AI performance, you now have a counterpoint. Context size drives memory demand. Memory hierarchy drives GPU utilization. ICMS solves memory bottlenecks for long context inference. If you're working with LLMs at scale, multi-million token contexts, agentic workflows, retrieval augmented inference, understanding where your KV cache lives is just as critical as understanding your model architecture. Subscribe if you want deeper dives into AI infrastructure, semiconductors, and high-performance memory design.